Welcome to the first of 2 units on exponential functions and logarithms. Let's first review some of the functions we've worked with in the past. Here we have a graph of a constant function, a linear function, and a quadratic function. The constant function, like f of x equals 2, is this horizontal line right there. The linear function, f of x equals x, makes this a line with a slope of 1. And the quadratic function, f of x equals x squared, makes a parabola. Now for the equation for a constant function, there actually is no variable. It's just a constant term, which is 2. For a linear function, we have an input variable, it's x, and the exponent of x there's nothing there, so that means it's to the first power. For the quadratic function, we have an input variable x, and it's being squared. It's being raised to the second power. For an exponential function, the input variable is the exponent. So let's take a look at that. So the definition of an exponential function is the exponential function f with a base of a is denoted by f of x equals a to the x power. As long as your base a is greater than 0 and not equal to 1, and x is any real number, so you can't have a square root of a negative number there. Let's take a look at a few examples of exponential functions and their graphs. Here I made a table, input-output table for a few equations. The first one is f of x equals 2 to the x power, so our base number is 2, and it's being raised to the x power. And in for x, I put a -3, a -2, a -1, 0, 1, 2, and 3. And 2 to the negative third power is 1 over 2 to the third, which is 1 over 8. 2 to the negative 2 power is 1 over 2 squared, which is 4, so 1 over 4. And 2 to the negative 1 power is 1 over 2 to the first power, which is 1 over 2. If you put a 0 in for the x, for our input variable, any number to the 0 power, as long as that base number isn't 0 itself, any non-zero number to the 0 power equals 1. So you'll notice in all of these equations, if I put a 0 in for x, the output is 1. But then we can go into our positive numbers where things start to go up pretty rapidly. If you put a 1 in for x, 2 to the first power is 2, 2 into x, 2 to the second power is 4, 3 in for x, 2 to the third power is 8, and then it will go to 16, 32, 64. It starts to go up pretty rapidly after that. The graph of f of x equals 2 to the x is this green line here. You'll notice that it goes up and it's going to continue to increase its slope as it keeps going on. You'll also notice to the left of 0, it's a little bit higher than these other two equations that have larger bases. So it's further away from 0 there. They all go through the y-axis at exactly the same point, y equals 1. And then 2 starts to level off this way. Now 3 to the x, well, if we change our base and increase our base, then all of the exponents are going to be larger at the same value. So 3 to the third power, for example, is 27. That's much bigger than 8. Even 3 to the second power is 9, which is much bigger than 4. So you'll notice the blue line rises up much more rapidly. And this line right here is just 2, and it's already much steeper of a slope right here than this one is. And it will continue to increase that way. And if we keep increasing our base, it will go up even faster. So this base is 5 to the x. Our base is 5, so 5 to the third power is 125. So if you just go over to 3, I would have to go all the way up to 125 on this graph to figure out where that 5 goes. Which would be really high considering this number up here is 6. So you can just imagine it goes almost straight up after 5 or 6. All of these exponential functions show a phenomenon called exponential growth. Now, in popular culture, you hear a lot of people say that things grow exponentially. And I don't know if they really mean that it grows exponentially as if the input variable is the exponent, or if it just grows rapidly. But we all know quadratics can grow rapidly too. It doesn't necessarily have to be exponentially. Exponential growth will have a exponent, that is your input variable, And then the base of that exponential function is called the growth factor. And so the higher the growth factor, the faster the exponential function grows. So these three functions show exponential growth. By making our input variable x negative, our exponential growth functions turn into exponential decay functions. So these are the same three functions. The only change is the exponent is now a negative. So 2 to the negative x, 3 to the negative x, 5 to the negative x. The values are actually symmetrical to the growth functions, but now instead of starting very close to 0 and then going to infinite style numbers, it starts at very high numbers, and once it crosses through 1, it gets very, very close to 0. So this shows exponential decay. Now our input and output values for these exponential functions, our input values are the same, but if I put a -3 into a to 2 to the -3, well, 2 to the -3, 2 to the -3 is 2 to the +3. That's why the result is 8. If I went back to -4, 2 to the -4 would be 16. But here we have 8, and then 4, then 2, then 1, and then it just gets closer and closer and closer to 0. Same thing with 3 to the -x. Starts off with 3 to the 3rd, and it just gets closer and closer to 0 until it's imperceivable, the difference between that function and 0 eventually. Same thing with f of x equals 5 to the -x. It starts at 125 now. Instead of that being the last on our table from the growth function, the decay function, it's where we start our table, and then it just goes back downward. Compound interest, or compounding interest, is the interest on a loan or deposit calculated based on both the initial principal and the accumulated interest from previous periods. Financial institutions use the compound interest formula to calculate the effect of interest on its debit and credit accounts, such as savings accounts and mortgages on houses and automobiles. The rate at which compound interest accrues depends on the frequency of compounding, so the higher the number of compounding periods, the greater the value of compound interest. In this equation, we have several variables. A is the total amount in the account after the interest has been accrued over a certain number of years, which is T. P is the principal, and that is the amount of money that is deposited or borrowed in the account at the start. R is the yearly interest rate the account receives, and N is the number of times the interest is compounded per year. The compound interest formula is an exponential function because we have exponents and t that are variables and can change over time. So if we extend the time, the number of years or parts of years, then an account is collecting interest, or we can change the number of times interest is compounded per year. And those are both variables that can change, and that makes this an exponential function. So here we have a problem. You deposit $8,000 in an account that pays 4.37% annual interest. Find the balance after 5 years if the interest is compounded yearly. Then do the same thing, compounding the interest daily. So first let us establish our variables. You deposit $8,000, so our P will be 8,000. That's our principal. That's our starting value. The interest rate, R, will equal 4.37%. But that's percent. We have to turn that into a decimal. I know there's a decimal on there already, but it's written as a percentage. So in order to make this into just a straight decimal, we have to move this decimal point over twice towards the left. So what that will end up being is our rate will be 0.0437. And that is the rate that we will use for this problem. And it says find the balance after 5 years. So our time is 5 years, or just 5 in our equation. Now the n changes. First we are going to do it yearly. So the first time we will say that n equals 1. interest will be compounded one time per year. And in the second time, n will be daily, which is 365. We'll ignore leap years for this calculation. So now let's fill out our formula with our known variable values here. So A equals P. So our principal is $8,000 times 1 plus our interest rate is 4.37%, which we, as a decimal, is 0.0437. Always use that decimal value when you're doing these calculations. And the number of times, well, the first, we're just going to compound the interest once per year. So we put a 1 in for n. And then our exponent is 1 times 5. Okay, so over the course of 5 years, we will compound interest once per year. All right, multiplying 8,000 times this exponential part of the equation, you will get $9,907.60. So you've earned $1,907.60 over the course of the 5 years just on interest alone. And that's compounding the interest just once a year. Now we'll do exactly the same equation, but instead of compounding the interest once per year, we will do it once per day, assuming there's 365 days in the year. So 8,000 is still our principal, and our interest rate did not change. But we're not going to just do this once per year. We're going to do it 365 times per year. And then that also changes the exponent to 365 times 5. So that exponent part will give us exactly how many times it was compounded over the entire 5 years. 365 per year times 5 years. So we also know that we're not compounding by the full 4.37% interest each day that we compound interest. It is 1/365th of that annual interest rate will be compounded. So by doing all this out, we should get a slightly higher number. Since our interest rate is only 4.37%, it's not going to be a hugely different number, but it will be different nonetheless. It will be $9,953.54. So just by changing the number of times that interest was compounded per year, the account will actually gain almost $50. This is a big moment. We are going to learn a new mathematical constant. So mathematical constants, you know a few of these. Now physics has hundreds of constants, but math, we have these 3 big ones to start off with. The first one you learned was pi. And remember, pi was the circumference of a circle divided by its diameter. And that always came out to 3.1415, and then many more numbers. It is an irrational number. It keeps going after that, and it doesn't repeat. And some people can remember a lot of those values, but if you know 3.1415, that will get you through most situations in math. And just remember, it's the circumference of a circle divided by its diameter. Then, earlier in this course, you learned about I. I is the square root of -1. And I is really important because normally in a problem, if you ever end up with the square root of -64, for example, you have to stop because there is no square root of -64. Not only that, it's not even a real number answer. What I allowed us to do was rewrite this as the square root of 64 times I. And then we could actually take the square root at that point, and that gave us 8i. And we can continue to work some math on this at that point. And in some cases, I will end up dropping out of the problem and we'll end up with a real answer instead of an imaginary answer. But now we're going to learn a new one, and it is the natural base E. It's also called Euler's number. Euler is spelled E-U-L-E-R, and it was named after the mathematician that first calculated its value. Now, E is another transcendental number like pi. It is a decimal that keeps going and doesn't repeat. It starts off with 2.7182818 to 8, ... and it keeps going just like pi does forever and ever. But where it comes from isn't as simple to discuss as the circumference of any circle divided by its diameter like pi was. We're going to have to really get into it to figure out where that number came from and why it's useful for us. So let's begin. Okay, here you see the graph of, or at least the positive values of the graph of 1 plus 1 over n to the nth power. And you might recognize this as an exponential function. So this is an exponential function. Not only that, it kind of looks a lot like the compound interest function. Well, there's a real good reason for that. But if you were to graph just this part of the function with the n's, we don't have the rate, we don't have the principal, we don't have the time in this. It's just the part that deals with compounding rates. It becomes this line that starts off at 1, like most exponential functions do, and it goes up, and then it kind of tapers out, and it seems like it doesn't go up very much anymore. It is continuing to increase, but just not that much. Let's take a look at this over a longer period of time. So here we have the same graph. I just zoomed in a little bit on the y-axis and out a lot on the x-axis. You notice it goes up and it kind of levels off right around where this blue line is. And this goes all the way out to 95. I could keep going with the line, but eventually it would be hard to tell the difference between the green line and the blue line. So I did it more in a table format. So over here, imagine I put a 10 in for the n's on this equation. So 1 plus 1 over 10 to the 10th power. My result would be 2.59374. The same thing with 100. I put 100s in for this n and multiply it out and then raise it to the 100th power. It would be 2.70481. Okay. I put 1,000 in for the n's, 2.71692. Put 10,000 in for the n's, 2.71815. So it's continuing to increase, but it's kind of tapering off. It's not going up by a lot anymore. It's just going up by very small amounts. 100,000, that's a huge number to put in there. It's 2.17827. So we only notice the change in the thousand after the thousands place. And then I put in, 1 million? And I get 2.71828. 2.71828. Now, this line right here is at E. And that is the line that this exponential function is approaching as it goes up to infinity. It will never quite get there, but it will always approach that. And that is where E actually comes from. So why is E important? And in order to figure this out, we have to go back to that compound interest formula. Now, the constant E was discovered by Leonhard Euler in the 18th century. Now, Euler was trying to solve a problem Jacob Bernoulli first proposed half a century earlier related to compound interest. Imagine you put money in a bank and that bank compounds the money at a rate of 100% annually. After 1 year, you'd have two times the amount you invested. So in this example, $5,000 will be our principal, our starting value. The interest rate is 100%, which is 1.00 as a decimal, so 1 over 1, which 1 over 1 is just 1, right? So 1 plus 1 is 2, and 2 to the 1 times 1 power is 2 to the first power. It's just 2 times 5,000. 2 times 5,000 is 10,000. So 100% interest rate, only one compounding per year, you'll get $10,000. If you keep the interest rate the same and just change the number of times interest is compounded to once a month, which is 12 times in a year, we will change the n to 12. By evaluating the formula, we now see that we have earned $13,065.17, which is over $3,000 more than if you'd compounded the interest yearly. By compounding the interest weekly, assuming there are 52 weeks in a year, you will have earned $13,462.98, which is over $3,400 more than if you compounded the interest yearly, and almost $400 more than if you compounded the interest weekly. By compounding the interest daily, assuming there are 365 days in a year, you will have earned $13,572.84, which is over $3,500 more than if you compounded the interest yearly, but only $110 more than if it was compounded weekly. The benefit of frequent compounds is less amazing between compounding daily and compounding weekly. We can continue to see the effect of compounding interest every hour, every minute, or every second until we come to continuously compounding interest every moment. What would the maximum benefit you could achieve by increasing the number of times interest is compounded? Well, we need a new equation for that. Continuously compounding interest will have the maximum amount of benefit of frequent compoundings. It's compounding every possible moment. So it will give you the maximum value in your account given any rate. And it actually has its own equation. Remember, we started with A equals P times 1 plus R over N to the NT. But when we were looking at E was the limit of 1 plus 1 over N to the N. And so if we substitute those parts of this equation out with E itself, we end up with the amount is the principal times E to the interest rate times T. And that actually is a simpler looking equation using E, and it will give us the maximum effect of compounded interest for any given rate of time. So let's say you deposit $4,000 in an account that pays 6% annual interest rate, compounded continuously. What is the balance after 2 years? So we're looking for A, and our P is $4,000. E is our constant, so we don't have to write that out. R is 6%, which is 0.06 as a decimal. And time is 2 years. Placing these values into our continuous compounding interest formula, we have A equals $4,000 times E, which is 2.71, to the R, 0.06 times time, 2. And if we multiply all of this out, we get $4,509.99. Not bad. Now that at those 2 years with 6% will have the maximum possible advantage of compounding interest. The interest is compounded every single moment. So even more than every second. And that would be the result of that. So while it's pretty cool that E is the value of continuously compounding interest, it doesn't really put it in the same category of importance as pi, but E really is as important as pi for other reasons. Y equals e to the x is the only exponential equation with which the slope of the curve at any given point on e to the x is e to the x. And the area under the curve from negative infinity up to x is also e to the x at any given point. So E, Euler's number, actually brings together all of calculus, since calculus very much is concerned with slopes of curves and areas under curves. So e to the x will only grow in importance as you begin to learn calculus. There are also many more formulas that include E. I will focus on 2 math formulas, even though there are much more physics formulas that include E. So e to the ix, that I is the imaginary unit, will equal the cosine of x plus I times the sine of x. That is one of Euler's formulas. And there's this creative formula, e to the pi I plus 1. So if you substitute pi in for the x's in that, you get e to the pi I plus 1 equals 0. And this is more of a clever formula than important. It has all 3 of the important mathematical constants that you know, e, pi, and I. And then it has the multiplicative identity 1 and the additive identity 0 in it. So it has 5 really critical numbers in math, all in the same formula, with a very simple solution. So that's pretty cool. Now that we've learned about e and exponential functions, let's look into solving exponential equations. If we are going to talk about solving exponential equations, we need to go back to the graphs of exponential equations. Remember the graph of 2 to the x, for example, started off low and went through the y-axis at 1, and then it went up exponentially high. And the important thing about this is every input value we had a unique output value. The output values weren't repeated. That's different than, let's say, a parabola, which you can pick many points on the parabola, almost any point on the parabola. Like this point here has an output value that is the same as the point over there, anywhere where a line would go straight through. So quadratics are not one-to-one functions, but exponential equations are one-to-one functions. Every output value is unique to a different input value, and they are not repeated. So with that being said, we can actually solve exponential equations if the bases are the same by setting their exponents equal to each other. So 3 is the base in 3x plus 1, 3 is the base in 3 to the 4th. Since those bases are the same, I know I can solve for the exponent by setting their exponent values equal to each other. X plus 1 equals 4, and by subtracting 1 from both sides, I get x equals 3. So if I were to substitute 3 back in for that x, 3 plus 1 is 4, 3 to the 4th equals 3 to the 4th. That's how you solve these exponential equations. But sometimes their bases don't appear to be the same. 2 to the x minus 1 equals 16. 16 and 2 are not the same number. But can you write 16 with a base of 2? And the answer to that is yes. I know 2 to the 4th power equals 16. So I can substitute this into this equation, 2 to the 4th for the 16. So 2 to the x minus 1 equals 2 to the 4th. I didn't change any values there. I just wrote the number 16 in a different way. Now the bases are expressed in the same way, and I can set the exponents equal to each other. X minus 1 equals 4, and by adding 1 to both sides, you get x equals 5. So in this problem, x would equal 5, and that would solve that exponential equation. But all exponential equations can't be solved this way. All exponential equations can't be written as two different exponential expressions with the same base. So in order to do that, we are going to have to develop a new way of writing exponents. All right, isolating variables in an exponential equation. Well, the variable is the exponent, and up until this point in math, you have not learned a way to isolate that variable very well. We know that 2 squared equals 4, and 2 to the 3rd power equals 8, but 2 to what power equals 5? Now, in order to solve this, we have to invent a new way to write an exponent so we can actually make that x something that's solvable. It's not as easy as just dividing both sides by something or taking the square root. That won't work when the variable is the exponent. We have to develop something called logarithms. Now, what a logarithm is just another way to write an exponent. It's not a new operation, it's an exponent. It's just a different way to write an exponent. And what it allows you to do is solve equations where your variable in the equation is an exponent, because we have no other way to do that right now unless we recognize it and get lucky. So what is the definition of a logarithm? Well, a logarithm, base a of x equals y. So a is the base to the y power equals x. So notice our base a becomes the base of the logarithm. This is read as log base a of x, x is the result, equals y, and y is the exponent. By rewriting a problem with a variable in the exponent, like 2 to the x equals 5, look, we have a variable up here, and we don't want it to be in the exponent anymore, so we can do some math to it. Well, we can rewrite that as log base 2 of 5 equals x, isolating the variable on one side of an equal sign, which is typically how algebra works and how we want it to keep working. So let's write some logarithms as exponential equations. So log base 2 of 8 equals 3. Remember, this is the base. This is the result. And this is the exponent. So base 2 to the exponent of 3 equals 8. That is how you rewrite a logarithm into an equation in exponential form. And all of these will be true statements. 2 to the third power does equal 8. 2 times 2 times 2 equals 8. So it's a true statement. The next one, log base 4. So our base number will be 4 of 16. 16 is our result. Equals 2. 2 is our exponent. The whole point of the logarithm is it isolates the exponent by itself. Next we have log base 3 of 1 equals 0. So the base 3, and the exponent is the thing isolated. So 3 to the 0 power equals the result 1. And that's true. Anything actually to the 0 power equals 1. I could have put any number down here except for 0. I can't put 0 there. 0 to the 0 power does not equal 1. But every other number I could have put down there to the 0 power equals 1. Oh, next we have a fraction. Our base is 1/3. So 1/3, and our exponent is -2. So 1/3 to the -2 power equals our result 9. Now we can simplify this a little bit, and we should. 1/3 to the -2 power. Let me eliminate that negative exponent. Remember, you take the reciprocal of the number that is being of the base number. So that is 3 over 1 squared equals 9. And 3 over 1 is just another way to write the number 3. So 3 squared equals 9, which is true. That's a true statement. We just wrote it with a negative exponent and a fractional base before. But we can easily convert it into something simpler. Here is a neater representation of all of these values. 2 to the third equals 8 is the same as log base 2 of 8 equals 3. Log base 4 of 16 equals 2 is 4 squared equals 16. Log base 3 of 1 equals 0 is 3 to the 0 power, which equals 1. And the log base 1/3 of 9 equals -2 is the base 1/3 raised to the -2 power equals 9. Okay, let's rewrite the equation in the logarithmic form. So now we have exponential equations that we are going to write as logarithms. So I'm going to write the word log. Remember, the very next thing is my base. So my base in this case is 3. It's the base number of my exponent as well. And then the whole point of the logarithm is to isolate the exponent. So we want that on the other side of the equal sign. So where does the result go? Right here. Log base 3 of 81 equals 4. Our exponent is isolated, and every other number is accounted for. All right, next we have 4 to the third equals 64. To write that as a logarithm, it's log. Our base of our exponent is 4, so the base of our logarithm is 4. The result is 64, and that equals our exponent value of 3. 5 squared equals 25. That means log base 5 of 25 equals 2. And finally, log base 2 of 128 equals 7. Okay, let's evaluate these logarithms. And we're not going to use the calculator to use these. I selected ones that won't require a calculator, which is good because I haven't taught you how to use the calculator with these yet. So log base 3 of 27, and I will just say it equals x for now. So I can rewrite this as an exponential function. 3 to the x equals 27. Now remember, logarithms are just a different way to write an exponent. It's not a new operation, it's just a different way to write an exponent. So 3 to what power equals 27? Well, 3 to the first is 3, and 3 squared equals 9. What's 3 to the third power? 3 times 3 is 9, 9 times 3 is 27. So our value for x here, our exponent will be 27. We have log base 2 of 32. We can rewrite that as an exponent. I'll say it equals x. So 2 to the x equals 32. And we know there's a lot of powers of 2. So 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. And 2 to the fifth is 32. So our x will equal 5. That is our missing value. Okay, finally, log base 6 of 216. Let's write it as an exponent. So 6 to the x power equals 216. All right, well, 6 to the first is just 6. 6 squared is 36. 6 to the third, what is 36 times 6? You guessed it, 216. So our exponent in this case is 3. Oh, I forgot this one. Nice. Okay, there are some special logarithm values. We actually already saw one of these. We saw the first one, the logarithm of 1. Now remember, our b, that's our base, and that number right there is the result, and our 0 is our exponent. So rewriting this in exponential form, b to the 0 power equals 1. And that's true always. Anything to the 0 power, as long as b does not equal 0. B cannot equal 0, but it can equal any other number. And any other number to the 0 power will equal 1, because any number to the 0 power equals 1. So looking back over here, 5 is our base. So 5 to our exponent, we don't know, equals 1. What exponent does that have to be? 0. Here's another one. Log base b of b equals 1 as well. Huh, that's kind of weird. B, let's rewrite that. The base b to the first power, anything to the first power is itself. It's the exponential identity. So log base 6 of 6 will equal 1, because 6 to the first power equals 6. Next, we will talk about the common logarithm. The common logarithm is a logarithm with a base of 10. And we call it the common logarithm because the number system that we use typically in math is base 10 number system. There's 10 digits before another digit is introduced. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10 digits. And then the next thing we have to do is add another digit, and we go back to 0 with the first digit. That's the reason why the normal logarithms, or the most used logarithms, have a base of 10. So if you ever see log base 10 of x, that could be rewritten as log of x. Or if you see something like log of 1,000, what they mean to say is log base 10 of 1,000. And we can actually figure that out. Our base is 10. Our exponent, we'll put an x there. But our result should be 1,000. So what power of 10 equals 1,000? Well, 10 to the first power is 10. 10 squared is 100. 10 to the third power is 1,000. So log base 10 of 1,000 equals 3. Why is that? Because 10 to the third equals 1,000. Next, we have the natural logarithm. The natural logarithm is a logarithm with the base e. So instead of having a number, like a whole number, it has the base e, which goes back to Euler's number. So log base e of a number x equals the ln of x. Ln natural log. It's almost like written backwards, like natural log nl, but backwards ln. There you go. So let's start to use this in a problem. So e to the x is 14. So I know that I can write this as a logarithm as log base e of 14. But that doesn't really help me out too much. I don't have a log base e button on my calculator, but I do have an ln button on my calculator. So here's the first one we're using a calculator to solve. If you have a natural logarithm and you need to solve it, ln of 14. Now this is going to be a decimal because remember our base e is 2.71. And so there's not going to be a lot of whole number answers to natural logs. But the ln of 14 on a calculator is approximately 2.63905733. You can't really see that point. There you go, 2.63905733. So most scientific calculators have an ln button on them. Typing in just ln of 14 and hitting enter, that's what you'd get. And it keeps going after that, but at least the calculators I'm using only has that many digits on it. 1, 2, 3, 4, 5, 6, 7, 8, 9. It only has 9 digits, or 10 if you count the decimal point. So there you go. That's what a natural log is. It's a logarithm with the base e. Okay, let's talk about the inverse properties of logarithms. So you might recognize this part right here, log base b of b. Remember, that just equaled 1. But the log base b of b to the x power, if you have an exponent after that normal result part, then the log base b of b to the x is x. So it's almost like this exponent just becomes the solution. Well, here's the deal. When you have an exponent up there like that, an exponent of the result of a logarithm can be written in front. It becomes x times the log base b of b, and the log base b of b is 1, so x times 1 is just x itself. So we have log base 3 of 3 to the 5th power. Imagine writing this 5 in front here, and then this whole part just becomes 1. So 5 times 1 will be 5. The inverse function also works with exponential functions. So if you have a base b raised to the exponent of log base b of x, so log base b is actually an exponent of the base b. Well, that all just kind of clears out and that exponent equals x. So 3 to the log base 3 of 6 equals 6. The result part here just becomes the solution. So let's just do a couple examples of this. 10 to the log of 6, that's the same thing as saying 10 to the log base 10 of 6. And this follows our second problem, part of this problem. And the 10 to the log base 10 of 6 is just 6. And log base 4 of 16 to the 3rd, it's kind of like the first one, but look, our base is 16. It's not 4, or like the result part is 16, not 4. But I can rewrite this as log base 4 of 4 squared is 16. So 4 to the 2 times 3, which is log base 4 of 4 to the 6th power. And since log base 4 of 4, all just equals 1, and this 6 can be written in front, that whole thing just equals 6. Now, how do you use a calculator to solve logarithms that normally have decimal answers that we can't solve? For example, log base 4 of 12. There is no integer power of 4, which equals 12. So if we are stuck in this situation where we have to solve this problem, how do you do it knowing that the answer is going to be a pretty intense decimal? Okay, in order to find logarithms with bases other than 10 and e, they can be written in terms of natural common logarithms using the change of base formula. Possibly one of the most important parts of all of this unit is learning about the change of base formula. It's how you solve for missing exponent values. You write them as a logarithm, then use the change of base formula to solve them. So how this works, log base b of a will always equal the log base c of a over the log base c of b. But notice these bases are the same c. So you can put anything you want there. You could put like a 10 in there for c's. And the log base 10 of a over the log base 10 of b. Oh, that would just rewrite like this. Log base b of a equals log of a divided by the log of b. Because that's base 10. You just can't see it. Or you can write it as like a natural log. Instead of putting a 10 in for these c's, I could put an e in for these c's. I could put Euler's number in. So then it would be log base b of a is ln of a over ln of b. And that is another way to solve this. So how will this work? So we have log base 4 of 12. I can rewrite that as log of 12 over log of 4 just by changing the base to 10. And I rewrote it using this formula right there. Okay, so log of 12 over log of 4. Here's where you need to use a calculator. Most scientific calculators have a logarithm button. So you type log of 12 and you get 1.07918 ... And that divided by the log of 4, which is 0.602059991 ... So if you divide those two numbers out completely, you'll end up with approximately 1.79248125. And that is because 4 to the 1.79248125 power is approximately 12. Remember, 4 squared would be 16, and 4 to the first power is 4. 4 to what power equals 12? It's going to be a number between 1 and 2, so 1.79248125. And we figured it out. Nice job, everyone. Okay, so let's evaluate some logarithms here. Log base 3 of 15. 3 to what power equals 15? Well, there is no power of 3 that equals 15. 3 squared is 9. 3 to the third is 27. This is going to be a decimal. But I can solve this using the change of base formula. Log of 15 divided by the log of 3. And that equals, well, it doesn't equal it. It's approximately 2.464973521 ... We know it keeps going. So 3 to the 2.464 power is approximately the answer for log base 3 of 15. Log base 2 of 6. I can also use natural logs for this. Like I can write it as ln of 6 divided by the ln of 2. And that will give me an approximate value that could be extremely accurate. That would be 2.584962501. So there we go. That is the approximate value of that. If I use a log instead of ln, it would have given me exactly the same values because I'm using the change of base formula. Using log, I would have changed the base to 10. Using ln, I'm changing the base to e. But either way, it gives me the same solution. Log base 5 of 10 is like the log of 10 divided by the log of 5. And log of 10 divided by the log of 5 is approximately 1.430676558. I suggest you use a scientific calculator that lets you calculate both of these at the same time. That way you don't have to deal with errors and rounding. You know that it will be accurate at least until the 8th decimal place. I'd like to thank you for watching my video on exponential functions and logarithms. Remember, this is only one of 2 videos. The next video we will delve into expanding and condensing logarithms, as well as solving logarithmic equations. Okay, see you next time.